Hello and welcome to another video. Today we're going to be doing count vowels permutation. And honestly, this problem is like barely a medium, so I don't know how it has a heart, but anyway. So given an integer n, your task is to count how many strings of length n can be formed under the following rules. Each character is a lowercase vowel. Each vowel may only be followed by all these things. So let's actually draw these out because we are going to use this. So for each A, it can only be followed by E. For each E, it can only be followed by A and I. For each I, it has to be followed by another I. For O, it has to be followed by I or U. For U, it has to be followed by A. And then we will also have one more key, and that's just like the empty string that we'll use for the first character. So for the empty string or none or whatever you want to use here, we'll use the empty string. We'll have every character here. Every character is valid. Okay. So for length 1, obviously you can only have one character, and for input 2, essentially what it's going to look like is you can have every single character as a starting character, right? So you can have A, E, I, O, U, and then we just have to look like which ones can these be followed by. So A can only be followed by E, so we can only make AE. E can only be followed by A and I, so we can have EA or AI, or EI, sorry. And I can only be followed by, or actually, I think I can be followed by anything other than I. Yeah, so we will replace this. So I can be replaced by A, E, O, U. Yes. So we can have I, A, I, E, I, O, I, U. And O can only be followed by an I or U, so we can have O, I, O, U. And U can only be followed by A. So how many strings is that? Well, we have AE, we have EA, EI, pretty bad writing, but so we have 3, 4, 5, 6, 7, 8, 9, 10. And essentially, this is going to be very easy DP, and pretty much let's write out our stuff for DP. So DP, you need 3 things, right? You need a base case, you also need, I forgot one more thing actually. So you need state, you need a base case, and recursive. And essentially, all we need for the state is what index are we on, right? Like what character are we actually on? And then what is the previous character? Because we have to follow all these rules, right? Like an A can only be followed by E, all these rules. So if we just keep track for the state of the current character, or the index, like how far are we in the word, and last character. Then we easily know like what characters have to be at this index, because let's say our last character was an A, then we know like this character has to be an E and so on, right? So we can essentially just take whatever the last character was, we can just store it in a dictionary, and we can get the value of whatever is in there, and those are all of the characters that can be at this index. And then when we recurse, so I guess let's actually do the base case first. So for the base case, what we want to have is when our word is complete, right? So if the index is length of the word, index equals n, then we would want to return 1, right? Because if we're counting the number of possible things that we can have in all those solutions, whenever you reach your goal, you want to return 1. It's like this is one possible combination. And for the recursive case, essentially we just have to look up last character in the dictionary, and then for all valid characters after that, recurse to them. And how would we recurse to them? Well, we just have some kind of result, and we'll just say like, we'll just add the DP of the next index and that character that we just added, so the new character we added. So for example, let's say our last character was like E, we would recurse to A, and we would also recurse to I. So we would do 2 recursions there and so on. So all you need to do is keep track of the last character, and this doesn't cost too much because there are only 5 or 6 last characters. So this is still going to be an O(n) solution because the last character doesn't cost you anything. So it's a very simple recursive DP. So yeah, like I said, I don't know how this is a hard problem, but that's pretty much all we need. Just we're gonna keep this transition state just to make it easier, so we don't have to like have like 50 ifs. We can just have it in our hash map, and then we're going to use that, and then we are just going to have the simple recursion of keep track of the last character, and then recurse to all valid characters after that, and update the last character to whatever character you picked. Okay, and now we can code it up. And so I wrote this ahead of time. So essentially we have a transition dictionary where for every character you have a list of valid characters after that. So if your character is A, then the list of valid characters after A is only E. For E, the list of valid characters after E is A and I, and so on, right? And then if you have the empty string, meaning you don't have a character yet, then every character is valid. So we're just going to use this so we don't have a bunch of if statements in our DP. So we're going to have a visited, and we're just going to have a very simple DP of the index and the last character, so we'll call that last. So if index equals n, that means we have our whole word, so we should return 1. Otherwise, if this is in visited, so if index last and visited, return visited index last. And finally, we will just get the characters that we need, so we can just say like result equals 0, and for character in, this is going to be transitions, and then whatever the last character was, right? So for example, if the last character was A, it would just be E. If the last character was I, we'd go through all of this. So whatever the last character was, transitions last. Let's take every single possible character we can recurse to, and we'll just do res plus equals dp of recursing there. So the index should be index plus 1 because we use another character, and the last character is that character we just picked. And that's pretty much it. Now all we have to do, so we do have to add the mod because our answer can be really big. So we can store this mod value, 10 to the 9 plus 7. And we will just say visited index last equals res on mod and return result, return actually this. And then we should be fine here. So now all we have to do is return dp of, so start at index 0, and the last character will be the empty character. I don't know, I might have to mod this by mod again. We'll double check that, but that's pretty much it. So we have our, we have our base case where we used up the whole word. We have our caching, and then we basically say like for every valid character, let's recurse to those, and we'll use that for the because if you didn't have this transitions, you would just have an if statement like, if it's A, then do these. If it's E, do these. So this is like cleaner. Yeah, so let's try that. Might have to also mod it by mod at the end. I'm not entirely sure. Let's take a look. Oh, no. So it looks like it's fine. And so it's like an okay solution. It's like average. So as far as like the time can't really be improved, I don't think. You can improve space here, and I'll just talk about it, but I'm not going to code it up. So essentially, the way to improve space here is so notice how every single recursion goes to index plus 1. So you can actually make this, I believe, an one space solution because you are only going to index plus 1. So it would be something like you would have like an m by n. You would have an m by n like 2D array, but the dimension you only need is the letters, which is like 5 letters. But the actual index you don't need because every index relies on the index after it. So you would have like an array of like 5 letters or something, and then you would recurse all the way down to, if you can use a space optimized DP by getting rid of this index dimension, and you can try that if you want, and that'll basically give you an one space solution. So let's talk about the space and time for this one. So for time for this is O of n, because this last, like I said, is only like 5 or 6 characters, so that's basically nothing. And then the index is the length of these, like n, so that's O of n. Yeah, and then all these operations are basically O of 1, and this for loop is O of 1 because, like I said, there's only a few characters in here, right? There's like 5 character max, so that's basically O of 1. And for the space, we are caching, right? So this index is O of n, and then the last character is O of 1 because, like I said, only 5 characters. And yeah, pretty quick and easy hard problem, so good to see that. Definitely, I'd say not a hard problem. And definitely kind of a cool one to practice your like adding up all the different scenarios for something to happen. So yeah. And yeah, it's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.